Today I'm going to show you how not to break machines, but for that, we're going to need to break one. Let's see. Imagine you have a car and you need it at any moment. It has to be ready for any emergency situation. To make sure that happens, you take it for scheduled maintenance, change the oil, the belt, the filter, and check the fuel. But have you ever stopped to think that sometimes you replace a part that was still good? An oil filter is relatively cheap, so you think, okay, better safe than sorry, let's change it. Now, imagine that in a factory. We've already visited several of them here on Bolivar. Instead of one filter, there are thousands. Instead of one engine, there are hundreds. And then, replacing parts too early can turn into a huge waste. But you also can't just wait for them to break and stop production. That's expensive too. So how are we supposed to know the exact moment to do maintenance? Today, we're going to find out how a company uses artificial intelligence and industrial sensors to figure out the exact moment when a machine needs attention. I'm at the Traction Artificial Intelligence Center, which has 10,000 repair shops. Here, they take real industrial machines and push them to the limit to generate data. This data feeds the artificial intelligence and helps the system learn how failures start. They monitor the signals that the machines emit all the time, because every machine, when it has a problem, gives off signals in a car. You notice it when it's already a bit late, right? It's a strange noise, some smoke, or a warning light on the dashboard, LD. But the goal here is to detect signals when you can still fix it by adding a bit more lubricant, making a quick part replacement rather than dealing with an emergency shutdown.
And the impact goes beyond the factory. Today, we monitor 250,000 machines live out in the field. And in this machine graveyard, each one of these machines taught us something about their behavior.
Every machine we're seeing here was purposely broken so Traction could study the failures. These failures mainly happen in parts like the motor, bearing, or compressor. When the problem is advanced, you can tell by the temperature. Because the machine heats up, they're going to run a test here now with 8 bearings. A bearing is this part. It's a bearing that holds a shaft. And these are all parts that are actually used in the industry. So each part is assembled in a different way, lubricated in a different way, precisely to create problems. And so we can learn from them. In just a few minutes of the machine running, we can see on the thermal camera that the bearing that was in worse condition is reaching 97, 98 degrees. Soon, smoke will start coming out. The friction kept increasing, and smoke started coming out. In a real factory, this could cause a fire. It could catch on fire. They told me that 80% of failures in industrial equipment happen due to lack of lubrication. So, you can't run out of lubricant, but if you do, this is what happens. You can't really see how hot this is because we can't show it on camera, but let's pour a little water on it so you can get an idea of music. We saw the machine heating up and realized there was a problem. But here's the thing, this sensor already knew about it long before we could see anything on the thermal camera or in the smoke. This is the traction sensor. It measures vibration, ultrasound, temperature, and the machine's magnetic field. Music. For a long time, the main way to detect this problem was by reading the vibration. If there was any change in it, you knew what could be tightened, lubricated, or replaced. But often, when the vibration changes a lot, it's because the problem is already advanced. It's like smelling smoke. When you smell that, it means something has already burned. And that's where another technology comes into this type of monitoring, which is ultrasound. It's a sound with such a high, sharp frequency that humans can't hear it. It's as if the sensor listens to vital signs, and they show up even before the vibration. But to reach this level of precision, the sensor itself also needs to be tested. And that happens right here. Music. This here is water. At 80 degrees, I'm starting to feel sorry for the sensor. It's alive. This machine creates a salty atmosphere like sea air, but in an accelerated way, as if the part had been exposed for several years. This here is a shaker, basically a shaking machine, but a very violent one. At 85 degrees Celsius and 97% relative humidity, it's a condition that we would never survive. The sensor can't just be smart. It has to survive all of this. It works in extreme temperatures, from -40 to 120 degrees Celsius, and it's also sealed against water, dust, chemicals. The idea is to be able to use it in any type of factory, and the sensor is installed directly on the machine with adhesive screws or welding, depending on the equipment, so it doesn't come off during use. But of course, I couldn't come here and not see a machine actually breaking down. So let's test this sensor in practice. This is going to be a shaft breakage test. There's a shaft running through here. It's about 7 centimeters in diameter. It's pretty big, but at the same time, a machine here is going to force the shaft. They're going to put a 10-ton weight on top of it until it breaks. Just imagine how intense that is. In this test, the belt is the one that's going to be sacrificed. It's this part here that connects one shaft to the other. All these examples I'm giving are things that can be identified by the sensors before they break. One cool thing you can notice here is that there are 2 motors. One provides force while the other acts as a brake. Similar to how an electric car works. When a motor is forced, it starts to generate energy, and then it slows down the movement. I think the shaft broke. Let's go check it out. The shaft in here is completely bent. Look, now you can see it. You can even see a piece of the bearing. And I can feel with my hand that it's extremely hot looking here. You can tell that a steel shaft, about 7 centimeters in diameter, snapped. It's impressive. Just in this test, they collected more than 50 gigabytes of data. So there's all the machine movement, vibrations, torque, temperature. Using these signals, the machine will learn that this is a symptom that a shaft might break. And with that, we can prevent it from happening in real life. The belt is already about to break. Look at the remains of the belt here. It's cool to see. But you don't want that to happen to me, right? Of course, I like to see things exploding, catching fire, but in day-to-day factory operations, we don't need to go to that extreme because the sensor already predicts the problem. It knew all this was going to happen before we could even see it. The sensor collects the machine's data and sends it to the cloud, and it works kind of like those apps that can figure out what song is playing. When you don't know the song, the app takes a small part of it and can already identify it, but if we look closely, it doesn't really know what the person is singing or which instrument is playing. What it does is take a small part, analyze it mathematically, and find a pattern. And then it compares that with a huge database that has lots of songs. And the sensor does something similar in practice. That's how it can detect failures. This is the extreme conditions test. There's a control bearing, which has no problems at all. Then there's one that's kept in an extremely humid environment near water. Another one with a heat gun, simulating a very hot environment. And the coolest one is a sandbox, where there's a blower that covers the whole bearing with sand. It's a very tough working condition. Here, it's already a motor soft foot test. One of the 4 motor mounts is loose. This will make it vibrate, misalign, and cause a series of problems. This is what the sensor picks up. It may look like a mess, but that's because there are several frequencies mixed together here. And then, using math, we can separate it into several different frequencies. Each one represents a part of the machine. For example, This one could be the vibration from the motor, the shaft, or the bearing. It's like the computer is listening to a song and can separate the instruments, the drums, the guitar, the bass, and then, when there's any change in these waves, you can tell which part is having a problem and what the problem is. This graph shows a machine wearing out over time until it breaks. So at first we have a healthy machine just needing maintenance, and later it already needs to be replaced. Ultrasound can detect any minor failure, which can be fixed by tightening a screw or some lubrication. When the problem is detected by vibration, you might already have to replace a part or something like that. And if the temperature starts to rise a lot, it's a sign that there's a serious problem. So what the sensor does is read this data and send it to an AI system that will compare it with thousands or millions of other readings that have been made to see if there's a problem or not. Many times, the sensor discovers failure patterns that no one had measured before. It finds a new way to detect a failure, and then it can give a diagnosis of what needs to be done and when it needs to be done. But the sensor alone doesn't solve everything. What traction does is create a priority map, which machine is more critical, which one can wait, and what to do in each case. It's like going from the machine has a problem to this specific bearing needs lubrication as soon as possible. When a factory's production stops, you don't see it, but you feel it in the price, the empty shelves, the delays. What we saw today is what happens before that. The invisible work that keeps everything running. The industry doesn't stop because there are people obsessed with understanding how things break, and he's one of them.